Boom. Hello and welcome back to Calculus 1, section 4.5, Linearization and Differentials. So we are going to learn how to approximate values and approximate change. So linearization is the first concept, and linearization approximates value of the function. Now you would say, well, can't I just compute? Sure, but sometimes approximations are better or faster, easier, because calculators are not around or whatever. So you are going to approximate ln of 3. Because I'm asking you, what is ln of 3? And you're just looking at me right now, right? Because you don't know. I don't know. But I know how to compute it using linearization, differentials, and on a calculator. So if the calculator is not around and I need ln 3, let's say, you know, we always paint the same picture. You are on a desert island, right? The batteries in your cell phone and the calculator have run out. The Wilson is gone. You have nothing else to do. So you calculate ln 3 by hand, right? I mean, by stick on the sand. So let's learn the procedure for it. So what is this linearization all about? We realize that it's much easier to compute in linear function, y equal mx plus b, than in whatever other function you have. Say you observe the square root of x function, and you want to compute square root of 3. Now, square root of 3 is this y value here, and without a calculator, not really clear what it is. But then you realize that next to square root of 3, there is a nice number called square root of 4, which is equal to 2, right? And if you find the tangent line at that number, which will look like this, square root of 4 is sufficiently close to square root of 3. Now, can you see what's happening here? Observe that the y value of y equals square root of 3, right, is close to computing mx plus b, where this one over here is x equals to 3. It is easy for us to find the tangent line without anything. And then I compute, instead of computing 3 in a square root function, I compute 3 in a tangent line. And that calculation can be done, stick in the sand. I don't need calculator. So it should be clear as I do this problem. So I want to compute square root of 3. Instead, find tangent line at square root of 4. And then compute 3 in the tangent line rather than in the square root function. Let's make that happen. F of x is clearly square root of x, because we are talking about taking square roots. We know that to find its derivative, we have 1 over 2 root x. And now, oh wow, I was supposed to say at x equals 4. There we go, much better. And now we compute Now we compute to find m, which is 1 over 2 root 4, which is 1/4. So I have slope already. Now I have a point 4, 2. I have a slope. So y equals, sorry, y is 2. And y equals mx plus b. Y is 2. M is 1/4. X is 4 plus b. And I have 2 is equal to 1 plus b. B is equal to 1. So here's the tangent line. Tangent line is y equals 1/4 x plus 1. So what I claim is that square root of 3 is approximately equal to 1/4 times 3 plus 1. So instead of computing 3 in the function where I can't compute without a calculator, I compute 3 in a tangent line which is obtained by working out the tangent line in a nearby point. So 3/4 is 0.75 plus 1 is equal to 1.75. So my calculation by hand for square root of 3 is 1.75. Now you're going to take your calculator and tell me 2 decimal places for square root of 3. $1.73. By hand, I'm 2 cents off. All right? 2 cents. That's it. Can't buy anything for 2 cents. So we start from the question, what is the value for square root of 3? And the answer is, batteries are dead, I have no clue. Aha, but I can find the tangent line at 4, which is close. Go to the procedure for the tangent line, obtain the tangent line, and now instead of calculating square root of 3, you take that 3 and you plug in the tangent line. The y value that tangent line gives and the y value that the actual answer is are very close. And you can see that on the picture over here. You see that this blue line almost goes to this black point. And the reason is they're 0.02 off. 0.02. That's why. So I computed the tangent line at the point where I can, which is at 4. Oh, that's what's so confusing. This is supposed to say 3, and this is supposed to say 4. Much better. Huh. There we go. Because you plug 3 into the square root, and you get square root of 3, which is a value here. There we go. So I compute the tangent line at 4, which is what I can do because square root of 4 is 2. It's easy. And then that tangent line, when I compute at 3 and square root of 3, you can see they have very similar answers. The next question can be, let's compute, say, ln of 3. You can do that. So how much is ln of 3? Well, the batteries are dead. Okay, fine, let's do it. The function that we are considering is ln x, right? And the number that it's close to 3, which we can compute, is E, 2.7. So the closest number. How about if I want ln 10? What should I take? If I want ln 10, what should I take? E? squared, right? E squared. It's about 9. It's good enough, right? So you look for the closest point that you can compute without any issues. So now the derivative is 1 over x, and the slope is 1 over e. So my x value is e, and the y value is when you plug e to the function, you get 1, right? ln of e is 1. So now I have y equal mx plus b, y is 1, m is 1 over e, x is e, plus b, b 0. Oh. Y equals 1 over ex plus 0. That's the tangent line. And now we know, instead of computing 3 in ln, we will compute 3 in the tangent line. So ln of 3 is approximated by 1 over e times 3, which is 3 over e, which is about 3 divided by 2.7, which is 30 over 27, which when you cancel by 3, you get 10 over 9. So ln of 3 is approximated by 1.11111 forever. When you divide 10 by 9, you get 1.1111111. All right, use your calculator. What do you say with a calculator? Do what? 1.09. Calculator. ln 3 is 1.09.
Because it's 1.09.
Give me four decimals. 1.0986. See? We're 2 cents off again. We did ln 3 by hand, and we computed this. So now you know how those log tables and that I talked about earlier came about before calculators. You can sit and do the great precision calculation this way, and then figure out the amount of decimals and things that you need. How about last one? How about let's do sine of some number of degrees. What should we do? Anyone? 1337. 1337. Oh, 337. Well, then we have to convert it down by 2 pi. You peel off. Okay, fine. 1337 degrees. It's okay. The full revolution of a sine is 360 degrees. So you have 720, and then 360 is 1080 degrees. So now 1337 degrees minus 1080 degrees is going to be 0, still 1, 8, that's a 5, that's a 2, so 250 degrees. 257, yep. 257 degrees. So sine of 100 is the same as the sine of 257 degrees. Now on the unit circle, This is 180 degrees, and this is 270 degrees. The one that it's in the middle is plus 45, 225 degrees. And now if we have those 30s and 60s over here, so 240, right? 240 degrees. So you look at all of these degrees that you have, and you realize that 240 is the closest to 257. Oh no, yeah. 57, or 270 is closer, yes, because it's 13 degrees. So 270 is closer. So we use 270 degrees because it's closest when you compare all others, right? You have 180 as important, 210 degrees as important, 225. So we have values for all of these in our head without calculator, I hope, right? So what I'm going to find is I'm going to find a tangent line at x or theta. Let's go theta. Theta equals 270 degrees. But there's one important thing that you must know. This has to be done in radians. You can't compute in degrees because the formulas and nothing will work. So must use, I'll put it in blood. Must use radians. So we are looking for tangent line at theta equals, and this is, yes, radians. Great. So now, the question that it's posed for sine of 1337 degrees is the same as if you are computing sine of 257 degrees. And now, because we can't compute that one, we're going to compute the 3 pi over 2, the tangent line. Now, we have our function f of x is equal to sine x, theta. F of theta is sine theta. And the y is equal to sine of 3 pi over 2, which is -1. So I have my point for the tangent line 3 pi over 2, -1. We are going to find the derivative. Derivative of sine is cosine theta. And we are going to plug in for m cosine of 3 pi over 2. And that gets us very good. So now we have the slope is 0, and the point is 3 pi over 2 and -1. Just -1. Tangent line is y equals -1, horizontal line. So now, right, worked out that way, unfortunately. So we are actually going to get -1 because it's sufficiently close. So now you can go and you can check your calculator. Make sure calculator is in degrees. Your calculator should always be in radians. And switch to degrees only when you need to. So sine of 1337 so my calculation says that sine of 1337 degrees is approximately equal to -1. Calculator says that sine of 1337 degrees is approximately equal to -0.9744. We are 2.5 cents away now from our calculation, as you can see. Yes.
You picked 240 instead. Would you have been off that up?
No, we would not be. Actually, that's a good point. Let's redo. Pick theta equals 240 degrees, and then convert that into radians. So 240 and 80 are both divisible by 60. We get 4 pi over 3 radians. So now we have that our theta is 4 pi over 3. We obtain the y value by plugging the 4 pi over 3 into the sine, right? Now 4 pi over 3, so all students take calculus, the answer is negative. And then pi over 3 is root 3 over 2. So we have root 3 over 2 as the y value, so point is 4 pi over 3, negative root 3 over 2. We find the derivative, f theta prime, which is the cosine theta. And to find m now, we'll use the cosine of 4 pi over 3. Now that's a half. Cosine is positive in the third quadrant. No, it's negative. It's positive in the first and the fourth. So it's negative 1/2. So there you have it. Y equal mx plus b. Your y is negative root 3 over 2. Your slope is negative 1/2. All of that is multiplied by 4 pi over 3 plus b. Now, 2 and 4 cancel. I have negative root 3 over 2. And then this is negative, so plus pi over 3 is equal to b. And now we actually have the tangent line, but this is exact, right? We can compute these things. Earlier, we learned that negative root 3 is about negative 1.75 divided by 2. Pi is 3.14, so this is roughly 1. You see? So I'm calculating this without calculator still. So negative 1.75 divided by 2. Again, I don't want to use calculator at all. Just all raw calculation here. 0.8 1575 plus 1 equals b. And here's the b. So b is 1 minus this, so positive 0.125. And the slope we said was negative 1/2. So the tangent line calculation worked out to be y equals negative 1/2 x, negative 1/2 x plus 0.125. Now, the issue with this is that you have to plug in radian angle. And your angle is 257. So now, in order to use this, must convert 257 degrees into radians, which is 180 degrees and a pi on top. So that's 257 pi over 180. Degrees cancel. So now you can say that the sine of 1337 degrees is the same as the sine of 257 degrees is equal to negative 1/2 times 257 pi over 180 plus 0.125. If you punch this in a calculator, you better get answer that it's close to other things. You know, maybe we did something wrong, but it has to be. So negative 0.5 times 257 pi (57). So 1/2 divided by 180 plus 0.125. Something is terribly wrong over here. What?
You got 2.117.
Yeah. Something is wrong somewhere, because we are getting negative 2.1 and we're supposed to get negative 0.97. So there is a calculation error somewhere. I'm not sure where. Divide by 60, you get 4, you get 3, 4 pi over 3 the theta. Sine of 4 pi over 3 is root 3 over 2. Oh, I know where it is. I'm missing a 2. When I cancel the 2 over here, there is a 2 that stays. It's 2 pi. So this over here is now roughly 2, which is a 2 over here, which makes this to be 1.125, which makes this 1.125. So we see that we didn't get the good answer, but we know this can't be less than negative 1. But this calculation suggests that the approximation gives us about negative 1.12. Now, we know that it cannot go more than negative 1 because the range is negative 1 to 1. But it's still close. I mean, this is approximation. Now, observe that when I used 270 degrees, we were 2.5 cents off, right? Because 270 was closer to what we were looking for than you wanted 240. That was further away. It is still close, but it's not as close as when you use the nicer, closer number, right? So we can't label this as wrong. This is approximation. We know, right, humans, right? We know that you can't have the answer to be less than negative 1. So negative 1.12 is definitely wrong answer. But you would actually have to scale this back and say negative 1, which is exactly what we got from the other one, negative 1, because you know that you can't have decimals after this because of the range issues. However, what I want to point out is that from 0.97 to negative 0.1 and from 0.97 to negative 1.12, that's what I want to bring up, that we use the closer angle and we got this gap, and we use the further away angle and we got this gap. But both of them are close. I mean, you know, both of them are close. And now it's time for us to just streamline this calculation and put the entire... So we did tangent line. We didn't learn anything new other than the concept that you go a little bit on the side to look for the convenient value and do the tangent line. So now let's streamline the tangent line. We call this linearization. So L of x is f of a plus f prime of a times x minus a. This is your tangent line done in one equation. So this is called the linear approximation. Near x equals a. So now, and I also have to make sure that you guys understand that this a is the convenient value, all right? So that's the 4 that we picked, 270 degrees that we picked here, the e that we picked for ln. So this a is your pick. You pick a convenient value. So a is the convenient value. That you pick to make the tangent line calculation easy and possible without the calculator. And then the rest is, yes, is that stuff. And we can now redo, let's do square root of 15 using linearization. So you want to compute square root of 15. What's a convenient value? 16. And the function is clearly root x, and the derivative is 1 over 2 root x, right? So all you need is to plug all of this into your linearization equation, and you got your tangent line right off the bat, and you just plug in 15. So L of x is equal to f of a, which is square root of 16, plus derivative computed at a, which is 1 over 2 root 16. And then x minus a, which is x minus 16. So all I did is I plugged in f of a, where a is 16, f prime of a, where a is 16, and then a is 16 for x minus a. Compute 4 plus 1 over 8 times x minus 16. 4 plus 1 over 8 x minus 2. And here is your linearization equation, which is the tangent line. L of x is equal to 1 over 8x plus 2. So how much is the square root of 15? It's approximated by 1 over 8 times 15 plus 2. So we found the tangent line. And we plug in 15, and now you can use, right, long division and stuff to figure out, you know, how much this is. So an 8 is 125, so this better be 1 point. I need to take 125 off, right? So 875 plus 2 is 3.875. Is that good? What does the calculator say? I need 4 decimals. 873. Because the next one is 9 and the next one is 8, so they will bring up 10. Look at that! We got the cents right. It's the 2 1,000 form. Now here's the big question. Can I recycle this particular tangent line, 1/8 x plus 2. Can I recycle that one now, since we got it, and compute this at 36? Like instead of 15. Square root of 36, which is 6. But can I? Can I recycle this tangent line? Can I recycle it for square root of 2? Can I recycle it for any other value? It will be terribly wrong, yes. It will be really off. It will be really off. Because you have to understand that once you have curvature, right? If you found your tangent line at this point here, there is a neighborhood around that line that works. A little bit to the left and a little bit to the right. Just imagine how terrible of a difference you have here. Look. Look at the distance between all of this distance is error. In my case, 1, 2, 3, 4, 5 squares. So instead of getting, let's say, 3.7, you have 8.7. That's terrible. So you cannot recycle. You cannot recycle equations. Every single square root that you have to find, you have to redo tangent line for it. Because you have to find the closest value, right? If you want a square root of 2, well, square root of 1 is closer than square root of 4. If you want square root of 3, you use the square root of 4 because it's closer. Make sense? If you want square root of 6, you use square root of 4. If you want square root of 7, you use square root of 9. Right? So you have to be careful. And every time it jumps on which square root you are using, the number as input, it changes your tangent line. Because it changes the x, it changes the y, and the slope changes, so the entire tangent line changes. It is done case by case. That's how it's done. And we're done with linearization. For linearization, you are using tangent line. The cool thing about this section is it introduced to you the notion of linearization and gave you the formula, right, where you do the entire tangent line in one shot. So you get all of the ingredients of the shopping list, right? You want to figure out square root of 15, so we'll use 16. The function is ln x, or root x, or 1 over x, or whatever the hell you have. Its derivative. And then 1, 2, 3 pieces of information. You plug them in. The linearization equation you memorized, and that's it. Now, do you have to memorize the linearization equation? No. You can just use the tangent line procedure. This is just made easy by placing all of the tangent line related calculations in a single equation. But as long as you know the concept that it's actually the tangent line that matters, you can just use the tangent line procedure and you're done. Differentials. This is the second part of the lecture, and differentials measure, approximate the change. So, linearization approximated the value of the function. So rather than computing ln3, you do the linearization and you find a number that is close enough. Differentials approximate the change. You see, when you wake up in the morning, you are tallest for that day. Because you've just been horizontal for a number of hours, all of the joints stretched. I mean, unless you slept vertical, leaned against the tree. I know someone who, after a 19-hour shift, did that. I had a friend who worked at Alaska. Apparently, it was awesome because there was nothing to spend the money on, but then you work double shifts and you make a lot of money. So after working 19 hours in a shot, he was so tired he didn't want to take the road home to the right. He cut through the forest, which is in Alaska. There's bear, and he walked through the forest, and then he woke up next morning leaning next to the tree. He actually slept a few hours leaning next to the tree. How tired he was. So yeah, but anyway, so unless you sleep vertically, leaning against the tree, or a house or whatever, you are horizontal, right? And your joints stretch. So when you wake up in the morning and get up, you are tallest for the day. And as you go throughout the day, your body weight will be compressing the joints slightly, and by the end of the day, you are shortest when you go to bed. Now, there is a function that models that, and then there is that very little change in height that happened. Another one that you can very easily relate to, you don't think about it, but is there, is driving. You sit in a car at point A, and unless you fill up the gas, when you arrive to point B, the whole system U plus car is lighter because you burnt the fuel, right? Now, those calculations are extremely important when you want to launch a rocket or fly airplanes or stuff like that, because the weight is a big factor, weight of fuel is a big factor for those kind of applications. So, it's undeniable that systems change in time. And instead of computing the exact change, which is, again, computing function values, which could be pain, we can approximate the change using the differential. So I'm going to say that exact change is y2 minus y1, which is delta y. And we don't want to compute that. We approximate change delta y with dy, and that guy is called differential. Now, where's this differential coming from? What is it? Well, it's a very simple manipulation of a basic fact that y equals f of x, all right? What I'm going to do is I'm going to apply Leibniz on one side and the Newton on the other. So Leibniz said dy dx, and the Newton said f prime of x. Well, Newton said f dot x, and then we changed that into a prime. I'm sorry? Well, y dot in his case, like that, like this. And then, yeah. So all we're going to do is to move this dx to the other side, and there it is. This is your differential. Oh, come on. So let's take a look at the simplest possible example. Approximate. I don't want to erase the word calculate. I want you to see that I used the wrong word. Approximate the change in x squared as x goes from 3 to 3.2. Well, we said that the actual change is approximated by the differential, and differential is given by the derivative times dx. Great. First, I have the change delta x, which was 3.2 minus 3, which is 0.2. This is your dx. Dx and delta x is the same thing, where dy and delta y are not the same thing. We also have that the derivative of the function is 2x. So now, dy is equal to f prime computed at 3, so that's 2 times 3, times 0.2, and we get 6 times 0.2, 1.2. So, approximate change is 1.2. Now let's check this. Exact change delta y is 3.2 squared minus 3 squared. Exact change is 1.24, and our approximated change, we did not use calculator, is 1.2. You see, for this change that we did, we didn't have to compute anything with 3.2. I mean, we had to subtract 3 from it, but that's trivial. You see that something like this today, with this computing power that we have, right, with calculators and things, where we can compute this quickly. Right? In the good old days, I really don't want to compute 3.2 squared, you know? Or if there is an engineering formula that has more of those obnoxious calculations. To calculate the change, it's much faster to do this. So what have I done here? I plugged in the derivative, which is 2x, and computed that to 3. That's 6. Times the change in x, which is x changed by 0.2. Boom, 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 boom. 1.2. Like that. So we can detect the change by doing these calculations. Now I can use these calculations to still compute root 3 and so on. You see, if I'm computing root 3, we know that we are going to actually compute root 4, right? So there is a difference between 3 and 4, and that's your delta x, and that's your 1. And you use the same procedure, you get the same stuff. So, to compute, let's do square root of 10. So you ask, how much is square root of 10? All right, so you know that your x is 10, and you want to change that 10 into a 9, because you can compute at 9. So what's dx? It's 9 minus 10. Sorry, 10 minus 9. Which is 1. You know that your function is root x, and your derivative is 1 over 2 root x. So the change in y is approximated by dy, and the dy is the derivative computed at the number we can do it, which is root 9, times dx, which is 1. So you get 1 over 6 there. Now, what does this mean? It means that the change between square root of 9 and square root of 10 is 1 over 6. It shouldn't take a lot of IQ to put it together now. Square root of 10 is approximated by square root of 9 plus 1 over 6. That's what it is. Because you know how to compute 1 over 9, and the change from 1 over 9 to 1 over 10 is approximated by 1 over 6. So, 3.66666667, whatever, right? Now, we take our square root of 10. Oh no, sorry, 1. 1, 6, 6, 6, 6, 6. And the calculator will give us a square root of 10 approximated by 3.1622778. We are about half of 1 cent off on the calculation. Now again, how the whole thing of differentials approximate the change when you go from one number to another number. So for instance, if your tire has a pressure of 24 and you want to go to a pressure of 30, the change is 6. 24 to 30, you changed by 6. If you were at one point in life 50 inches tall, and then at another point in life you're 70 inches tall, you grew 20 inches, the change is 20 inches, right? So it's just a simple subtraction between two numbers. So now, if I want to compute a number, ln 10 or root 10 or sine 15, whatever, if I want to compute a number, I pick a number that I can compute, like that, and then calculate the change between the two numbers. So to go from 10 to 9, change is 1, right? And then the function takes the shape of the problem. It's ln x or root x or 1 over x or whatever. And then the derivative is whatever the derivative has to be. So you compute the change first, approximate the change. You don't want to compute the exact change, because if you're computing exact change, that means compute root 10, which is what you don't know. So you're approximating the change. Approximated change is the derivative computed at the point you can do times the change in x, which is 1, and we get 1 over 6. And now common sense tells you that you need to add 1/6 to root 9, because root 9 is less than 1/10. You have to bump up. So root 10 is approximated by root 9, again, the point you can figure out, plus whatever the change is approximated there, and as you can see, it works out. So now you should go and try ln, try trig, or whatever makes you happy. One word problem, and we are done with this section. Then we'll hit the last section. Is very short, luckily. They have ideal gas law here, or change. I always do this change in atmospheric pressure because I don't have too many choices here. I only give you 5 word problems. They're very skimpy on this. $36 for 50th time in my life. Approximate the change in the atmospheric pressure when the altitude increased from z is equal to 2 kilometers to 2.01 kilometers So that's technically you go 10 meters up. And pressure in terms of the height is given as 1000 E to the negative Z over 10. So delta Z, which is the dz, is 0.01, right? Destination minus the number. And now we need the derivative. So 1000 e to the negative z over 10 times negative 1 over 10 as a chain rule. So it works out to be negative 100 e to the negative z over 10. dp, well, delta p is approximated by dp. Again, the actual exact change, is approximated by the differential, and differential is equal to the derivative computed at 2, so negative 2 over 10, times the change of 0.01. And the change is now equal to negative 10 e to the negative 1/5, which is negative 10 over 5th root of e. So they wanted to approximate the change, right? Atmospheric pressure as the altitude goes, right, from 2 kilometers to 0.01. And there it is. That's the approximate change. Now you can go and figure out what is this decimal here. So that's negative 10 divided by e to the 1/5. Or negative 10 times e to the...
The negative how is it about the negative zero? Yes, I just put that in the derivative function.
Oh. Yeah. It's supposed to pass 100, so this is just a negative 1, right? So there's negative e. Alright, good. So e to the negative e to the negative 0.5, 0.2. Negative e raised to the negative 0.2. Negative 0.8187. What's exact? Exact is when you take 2.01, plug it here, compute, take 2, compute, and then subtract 2. Right? Because the exact is given as y2 minus y1, in this case p2 minus p1. You can get exact change. But then again, do you really want to compute with that negative 2.01 divided by 10? Right, this is much faster. And it's good enough in approximation. Ta-da! Differential. Done deal. We'll restart for the mean value theorem.